Hello, welcome to numerical ship and offshore hydrodynamics. So, today we are going to discuss on IRF based solution. Okay. Now, in IRF based solution, if you remember in my last class, we have derived one equation of motion, right. Now, this equation motion includes the effect which is called the memory effect. So, we have based on considering this memory effect, we have come up a equation of motion. So, today we are going to discuss much on this equation of motion. Okay. This is the keywords that we are going to use to get this lecture, fine. So, without much delay, let us jump into the solution. Now, if you remember that in last class we finally arrived a equation of motion which may be written in form of now again I am dropping all modes of motion considering a single degrees of freedom equation of motion. So, it should be m plus a into x double dot plus minus infinity to t. So, it is then beta, it is t minus tau into x dot tau d tau plus C x is equal to the external force F. So, this is what we got, right. Now, if we include here the 6 degrees of freedom equation of motion. So, if I include all this degree, so then actually the same thing actually you can write in form of a summation. So, if we write this, then it should be like this. So, summation we can say it is j is equal to 1 to 6 and then it is m I j plus a I j into x double dot j plus minus infinity to t beta I j into t minus tau into x dot j into d tau plus C I j into x j equal to f of I, where I also runs from 1 to 6. So, this is the we can say this is the complete equation of motion using impulse response function. Now, why I call this impulse response function? Because here this function we can call the impulse function. Okay. Now, this equation also we can little bit change the limit minus infinity to t. So, now we can further modify this limit also by right changing the coordinate system. Like if I take let us take t minus just make it bigger, t minus tau, let us take s. Now, if you take like tau equal to minus infinity. So, it becomes s becomes your infinity. Now, if you take tau equal to t, then your s becomes 0, right. So, therefore, if you do here you can check that this becomes j equal to 1 to 6, then m I j plus a I j into x double dot j plus here you can take that if you now change the limit from s to j. So, therefore, we can get here it is at t equal to tau equal to minus infinity, s equal to infinity. So, it is infinity to 0 and then beta into s into x dot j. Now, it is become tau equal to t minus s, t minus s here it is t minus s ds plus C I j x j is equal to f of I, right. So, and also here you d tau equal to minus of d s. So, therefore, here instead of plus sign we have the minus sign. Now, what I am going to do is I am going to shift the minus infinity to 0 to infinity. So, if I do that, then minus sign become plus sign, and then finally, we are having j equal to 1 to 6 into m I j plus a I j into x double dot j plus 0 to infinity into beta s into x dot j. Okay, I just miss I j here. So, I just do I j x dot t minus s into d s plus c I j into x j equal to f of I, right. Okay. So, after doing this, finally, we are having a new equation. I mean, equation is the same, I just change the integration limit for my convenience only. So, then finally, we can get this equation of motion is j equal to 1 to 6 m plus a I j x double dot j plus 0 to infinity beta I j, it is t minus s, sorry, it is plus integration of 0 to infinity, it is beta I j. Now, it is s into x dot j, here we have t minus s into d s plus c I j into x j is equal to f of I. Now, again people really do not want to see here s. So, again you just simply change s equal to tau, and then we can get the same equation as summation j is equal to 1 to 6 m plus a I j into x double dot j plus 0 to infinity beta I j. Now, here it is tau into x dot j t minus tau d tau plus c I j into x j equal to f I, and here of course, I is equal to 1 to 6. Now, this is we call the impulse response function, the equation of motion using impulse response function. Now, if you look at the previous day lecture, that this getting a I j or getting b I j, these are really tough, right, because we can, if you see in the our last class, these expressions of a I j, the expression of beta I j is really very difficult, right. But then what is the advantage of using this impulse response function equation of motion? I mean, how we can, what is the advantage, and like why we are doing it, right. We have the frequency domain solution, we know how to solve it, and then what is the advantage of using this equation, right. So, before we discuss all these things, now let us try to find out how we can get these terms a I j and then b I j easily, right. Now, in order to do this, to get this a I j and then b I j, we need the solution in the frequency domain. Suppose I have a frequency domain solver with me, and then I have some added mass component a I j. I mean, now remember that when I call a I j, it is in frequency domain, when you use the small a I j, and when I use the impulse response function a I j, I use the capital A I j. Now, this is, it is for the frequency domain. And then this capital A I j we use for the time domain, or we can call it is with the impulse response function. When I call the small b I j, it refers again for frequency domain. and when you call this or capital B I just sometimes we call beta. So, to make this more consistent, let us call not beta, let us call B instead of beta. So, when you call the B I j, it is again the referring to the time domain, and we are trying to say it is based on the IRF based solution. So, we need to understand this nomenclature. Okay. Okay, fine. Now, once we understand this, let us again take a single degree of freedom of equation of motion. So, I am taking 1 degree of freedom equation of motion. So, I just write 1 DOF 1 degree of freedom equation of motion in frequency domain. Then how it should look like. Now, if you know very well the general equation of motion is m plus a into x double dot plus. Now, here I just since the general equation of motion again I am using capital A, but eventually I make it a small when you use the frequency domain assumptions. Okay. So, again b x dot plus c x equal to f. So, this is the standard format that we are using to get the equation of motion, right. That from our very first day we discussed this, right. Now, here I am assuming the motion x is harmonic. So, I can make this equal to some amplitude xi a into cos of omega t. Okay. Now, if I do that and then I can make that x dot equal to minus of xi a into omega into sine of omega t, and then this x double dot again it is minus xi a into omega square into cos of omega t. Now, without loss of generality, let us drop this xi a and let us make it equal to 1. I mean it is it will not harm in the final solution, okay. Because here we are going to compare this frequency domain solution with the IRF solution. So, for sake of generality or sake of simplicity, I mean we just drop this xi a, instead of xi you can put 1. So, but if you want you can keep xi a and you can get the same equation, does not matter. Now, if I substitute this in this equation, then what we get? So, now this is my this is for my acceleration. So, it definitely it is minus omega square into m plus a into cos omega t, right, the first term, and here if I substitute with the x dot it is minus omega. Now, here I must use the small a, right. So, I just cut this and instead of I writing the small a, because I am using the frequency domain. So, instead of capital B also let me use the small b over here, and then it is sin omega t, and then now instead of capital C I am using small c into again cos omega t, and here I can write f of omega just to say that it is in the frequency domain. So, now what I do is now I just compare, I mean or not compare actually, I am now taking this cos component together, sin component together. Then I can have here it is minus omega square m. Now, I need to remember it should be small a, right, minus omega into not omega, it is plus c into cos omega t, and here I have minus omega b into sin omega t equal to f of omega, right. So, then I have this term, just need to remember I have this term minus omega square into m plus a plus c. This is the term which is having with cos omega t, and I have minus omega into b and this is the term I have with my sin omega t. So, I need to remember this. Okay. And then I have this impulse response function equation of motion, which is m plus a into x double dot plus 0 to infinity. Now, I just use the b because t minus tau. No, it is not t minus tau. If you use the 0 to infinity, it should be b tau into x dot t minus tau into d tau plus c into x equal to your f. Now, here I can make f of t, not omega. Again, take the same solution, we take, let us say x equal to some cos of omega t, right. So, therefore, x dot I can take, it is cos of it is minus sin of omega t. Now, here I have x dot t minus tau term. So, I am using x dot t minus tau, definitely it is minus sin of omega t minus omega tau. So, therefore, I can again write x dot t minus tau should be equal to, now it is sin a minus b. So, it is minus sin of omega t into cos of omega tau and then minus cos of omega t into sin of omega tau, right, because I am using sin a minus b, sin a cos b minus cos a sin b, right. And now, nevertheless, that x is nothing but equal to, again it is cos t. So, x double dot should be is equal to minus omega square, again it is cos of omega t. So, now I have everything with me. Now, I need to substitute the whole thing in this equation of motion, right. Now, if I substitute whole thing into the equation of motion, so let us see that what actually we can get. It is, I know this part is a little bit mathematical jugglery, but at the end we will get very nice thing. Now, it is m plus a, it should be minus omega square into cos omega t. So, it is minus omega square into cos of omega t. Now, plus 0 to infinity, we have, okay, all the time I am just writing beta, just my habit. So, it should be beta, not beta, whatever, it is up to you. Now, again it is x dot t minus tau, I just substitute over here. So, what I get? I include this minus sign, so it should be minus sin omega t into cos omega tau, then plus cos omega t into sin omega tau into d tau, right. And then I have finally I have the c into cos omega t. Now, again here up to this point again I need to separate out my cos omega t term and then sin omega t term, and then we need to compare. So, now if I take that what is the related to the cos omega t term. So, here I can get minus omega square m plus a, and from this second term this is the term actually I am having with my cos. So, therefore, it is plus 0 to infinity b tau into sin omega tau d tau. So, this is the term I am, and of course, I should not forget which plus c, which is with my cos omega t term. And then what is left for the sin omega t term? So, this is something it is with my sin omega t term. So, perhaps I am missing here some omega, because if you differentiate this, so some omega will come out here. So, this omega will be here also and this omega will be here also. So, therefore, it is minus omega into 0 to infinity, it is b tau, and then it is sin omega t terms, it is cos of omega tau into d tau. So, this is the term related to the and then this should be term related to sin omega t, right. So, now if you look at my previous, I have term this one, and then if you look at the next time, this sin omega t term having with the this term. Now, I need to compare this sin omega t term and the cos omega t term. Now, if I now here, now I know this. So, let us go back previously, and then this sin omega t, in this case it is minus. Now, if you look at it, it is minus omega b tau into this term, right. So, therefore, I just simply write it is this into minus omega into it is 0 to infinity into b tau, and it is with cos omega tau into d tau. Now, this is the term with related to the the damping coefficient, right. So, now here, so I get one relationship which is small b is equal to now again if I now here if I just cut out this this omega, this and this. So, then finally, we have b equal to 0 to infinity b tau into cos of omega tau into d tau. Now, here I know that if I use this Fourier transformation, so b tau equal to nothing but 2 by pi into 0 to infinity, it is b omega into cos of omega tau into d omega. Now, you see this is the equation after everything I am getting. So, this is the equation which actually gives you a nice thing, a relationship between the frequency domain damping coefficient b omega with the time domain damping coefficient b tau. Now, therefore, at least from this point I understand it is very difficult to find out the term b tau from that classical, that equation that actually we have derived in last class. From there getting b tau is really difficult. However, if you have the knowledge of frequency domain that the damping coefficient b omega, so you can using this b omega you can really get the value for b tau, right. So, therefore, from IRF actually one has to understand that to get the solution with respect to IRF, I must have the frequency domain solutions, right. If I do not know the knowledge of b omega, I really cannot use, let us say give a equation name, let us say 1. So, I cannot really use the equation 1 to get the value for the b tau, right. So, essentially this is now the question comes, right, like what I asked before, that what is the point? I have the solution for b omega anyway to solving this frequency domain panel method, and then why you are doing such a mathematical jugglery and come up with something that it turns out to be, if I do not have the knowledge of this, then I cannot get the other one, and then what is the difference? Nothing, it is simply a Fourier transformation, right, at the end. Then what is the catch? Then why people are doing this and using this very commonly, and you can see that there are lot of work available. For example, right now I can give you one reference which is Orcaflex, where we can use this IRF based solution to find out many things. Now, definitely it has some use, right. So, and we are going to, of course, we are going to discuss that knowing that without the help of B omega, I mean the frequency domain panel method, we really cannot do anything in this IRF based solution, but still why we are doing it, right. Anyway, we discussion that we can discuss in the next class, but today let us complete the whole thing, and then we need to compare the cos omega t as well. Now, if I compare the cos omega t, now if you from here I can get minus omega square m plus a. So, let me write it. So, it is minus omega square into m plus a. This is I am getting from the frequency domain. Okay, it should be small a. All the time I am making this mistake, very sorry. Okay. So, it is minus omega square into m plus a, and of course, even probably we don't write this, we don't use this c, because anyway, because this c is or this c is nothing but the the restoring coefficient which is same. If we use the time domain panel method or using IRF, or we are using the frequency domain panel method, this C is always a geometric property. In for example, in case of a heap, in whether irrespective of what the method you are using, it is definitely it is rho g into water plane area. We know that. So, therefore, that is why I am not writing the C. In fact, we do not need to write the m also, because the mass also the same. So, therefore, here actually really we can ignore this term the m also, right. So, from the frequency domain finally, the only the minus omega square into small a it should be enough. Now, let us see what I write if I do this for impulse response function. Now, here I understand that I can ignore this mass, I can ignore this C also, but remaining thing I need to write. So, therefore, if I write this, it should be minus omega square into capital A, if you see that, right. So, this term, and also I need to write this. So, therefore, I must write plus, just copy from here, 0 to infinity b tau sin omega d tau. Okay. Fine. Okay, and here probably I need to have one omega, right, because this second term coming from this velocity. So, I have this omega. So, definitely I can have a omega over here. So, therefore, this term I must have a omega. So, I just divide this. So, I will get A equal to minus A plus 1 upon omega 0 to infinity into b tau into sin of omega tau into d tau. So, this again the second equation here, again we can see this second equation having the relationship between this A frequency domain added mass with the time domain added mass capital A. Okay. So, so here minus A, I am sorry. So, with this equation let us call 2. Now, from equation 1 and from the equation 2, I understand very well that I can get the b tau, which is the time domain damping coefficient, and also the A, which is the time domain added mass quantity through the equation 1 and 2, right. So, again the question remain that why we are doing it, right, because anyway to get these two things we need to have this the frequency domain results, right. So, since we have the frequency domain result with us, why we are again we need to do all these things. Now, here the I mean we definitely going to answer this in the next class of course, and of course, next class we are going to discuss that how actually we can numerically find out the b tau and then capital A, but here I can modify this equation to very quickly, because this is the equation, it is actually this equation is for all frequency it is possible. So, when omega tending to infinity, then also you can have the this equation is hold very well. Now, if you put omega tending to infinity, so this second term this goes to 0 and then we are you are finding out this A is nothing but A into infinity, right. So, this equation 3 actually you are going to use, and that is why in impulse response function this A is not frequency dependent, we call that infinite frequency infinite frequency. So, now if I able now I am able to write the equation of motion using impulse response function. So, how it looks like. So, now I understand this added mass, it is A infinity, right, that is what I find out from the relationship. So, now m A plus infinity plus 0 to infinity into b tau into x dot t minus tau into d tau plus c into x equal to f, and I can call that f of t, right. When this A infinity understand that infinite domain added mass, and also I can get this b tau from the relationship 2 by pi, it is 0 to infinity b of omega cos of omega tau into d omega from this equation. So, this completes the solution using impulse response function. Okay. So, today we are going to discuss this much, and from the next class we are going to how we can solve this numerical I can get this b tau, this A infinity etcetera, that definitely we are going to discuss in the next class. Okay. Thank you.